All right, before we get started, so we're about to jump into chapter 2, which is differentiation and derivatives, one of the most important things there is in calculus. Anybody have any questions about anything we've done previously before we jump in? All right, so many of you probably noticed on Canvas I graded the first quiz. The grades are in Canvas. If you turn in a hard copy, I have them. So if you can stick around after class a bit and get yours back, that'd be good. I will post the solution to the first quiz and really all the quizzes sometime soon. There were a couple of people who needed a couple more days on it. So I don't want to post it until I give them a chance to get that in. Just a reminder, if for any reason, I think I made a lot of, obviously there's a lot of emphasis I made on COVID related reasons why you might need extensions on stuff, but really if you have any reason you need support or an extra day or two, whatever, let's have that conversation. Those of you who have asked me, thank you for letting me know of your situation. I haven't said no to anybody yet, so please, if you need something, let me know. All right, let's jump into chapter 2. It's about derivatives and rates of change. So we have used this example. I think this is the very first thing I showed you on day 1, talking about this example here. So S of t there is a function that describes the distance that a rock falls in free fall as a function of time. So t is in seconds, s is measured in meters, and I want to find the speed. So something we talked about before, and I'll give you a couple examples here. We talked about doing this, finding when t equals 0, we know that s of 0 equals 0. And I might have you remind me of the number, but I think we said at 5 seconds, someone correct me, but I think that's okay. 124.5 pounds. 5 times. Okay. I know what I did wrong. So if I have those 2 points, I'll just draw a quick graph here. I know what parabolas look like. So I can draw a quick sketch here. This point right here will be 0, 0. And this point out here will be 5, 122.5. And if I want to find the speed, what I can do is, even though that's not a straight line, I can connect those points to the straight line and find that slope, right? I think that was kind of what we talked about doing before, right? But that will not give, that'll give us something of a guess. It won't be very reliable. So what I would really like to do is, instead of having this point, this first point be 0, 0, I would really like to slide this point up closer and closer so I can get better and better estimates for that slope. And I'll draw a couple more of these lines here. One thing I think I said before was, if you just take that whole time interval from 0 to 5, the speed you get is actually going to be pretty low, because at the very beginning, at time equals 0, I have no speed. And for the speed is always increasing. So if I average in all those low speeds, I'm going to have a pretty significant underestimate. So what derivatives are going to allow us to do is to find that speed, that rate of change more exactly. In fact, it's going to help us find it exactly. So as these points, so these bottom points I'm drawing here, started at 0, but I want them to slowly get closer and closer and approach what value of t? 5. So what kind of, think about what we've been spending the entire 2 weeks on so far, is the idea of a limit. I want those 2 points to be on top of each other. But if you remember how to calculate a slope, s of t2 minus s of t1 over T2 minus T1. That's my slope, right? What happens if T1 and T2 are the same? I divide by 0, which I can't do, right? But what I hopefully can do is this, the limit as T1 approaches T2. Maybe that'll exist. I know that I can't just have T1 and T2 be equal, but maybe if I can find that limit, I'll get a slope. So just setting the stage for what we're doing today. We'll just think about what a derivative is. So I want to find let's look at another parabola. I want to find the equation of a tangent line. And while I'm drawing a graph, has anybody heard this, this phrase before, a tangent line? Few of you? What does it mean? A line that comes out of another line. It only touches at one point, right? So, I mean, this is a curve I've drawn here. I can draw a line that touches this curve at only one point, pretty much wherever I want. Let's say, so the point I care about is right here, though. Let's say that's 1, 1. I want a line that touches there. Again. Not perfect, but better. So I have a straight line that's going to touch that point on the curve. It's going to touch nowhere else. And I want to find the equation of that line. So let's just write down my goal here. I want y equals mx plus b. I know what x is. I know what y is. I gave you both of those things. So I keep talking about this derivative and slope as a rate of change. So the next thing I'm going to go for is that that rate of change, that slope. So I'm sure you've all seen this more times than you can count, but this is basically what we're going to be using here. At least for this example, I want to find the slope of this line. I care about, really the only points I care about is this base point 1, 1. So I'm going to let those coordinates be fixed. I'm going to let this other point look like this. I want x2, y2 to be completely generic. So it'll just be x, f of x. So if I try to find the slope like that, then here's what I get. Slope is equal to f of x minus f of 1 over x minus 1. But like I said, I really only care about what happens when x is equal to 1. Can I just set x equal to 1 though? Yeah. I got one vote for yes, I can. If I have x equal to 1, I'm going to have a division by 0 problem, right? So this will certainly not exist when x equals 1, but maybe this will. The limit as x approaches 1 of f of x minus f of 1 over x minus 1. Maybe that limit will exist, and that'll be helpful. But in general, that function's x squared, right? How about this limit? We may have even looked at this exact one before. Does this limit exist? Better yet, how can I start trying to look for it? I could plug in numbers, certainly. Is there anything else I could do? Something algebraic. Okay, yep, it factors. All right, now what can I do? Right. Now, I have this thing. Can I just plug in 1 now? Absolutely. Polynomial, I know polynomials are continuous everywhere, so I can just get their limit if I can evaluate it x equals 1. So all that work I just did to find the slope, right? I should probably pause there. Any questions about how I got this far, at least? Okay. So, I mean, if you just kind of look at the really rough freehand picture I drew, hopefully you were expecting a positive slope, steeper than 1. So hopefully 2 seems reasonable. Let's get the rest of this equation now. So I know that y equals mx plus b. I'll just put it down again here. I gave you that y was equal to 1 and that x was equal to 1. We just discovered that m was equal to 2. So that gives us that b is equal to -1. So this tangent right here that I got is x, not x, 2x minus 1. Did I do it wrong? Oh, I just solving for b here. Yep. And again, for my picture, I got a y-intercept that fell below the x-axis. So I was really only able to find this limit because I gave you a specific point where I knew that I would get this limit. I would really like to be able to find derivatives and slopes like this, no matter what my functions look like, no matter what the point I give you is, things like that. So we need a more systematic way to get there. So the way we're going to develop that up is through, I advanced too far, is this the idea of secant lines and tangent lines. So tangent line, it sounds like a few of you have heard of. Secant line is maybe a little more obscure. So let me just draw an arbitrary looking curve here of x equal a. I'll have 2 x values, a and a plus h. And h is just going to be, you know, how far apart these are. And these 2 y values are going to be f of a and f of a plus h. So without calculus, all you can really do is, you know, join these 2 together with secant lines. And what a secant line is that you just take 2 points on a curve, connect them with a straight line. And as long as you know where those 2 points are, you can pretty easily calculate the slope. I've been doing that for a pretty long time. But now what I really want is, here's my goal. Find slope of curve at x equals a. Not between a and a plus h, but just where x equals a. So if I draw that secant line, I can definitely find that slope. How would I find the slope on that secant line? Yeah. Okay, what are those top and bottom coordinates? Okay, so f of a plus h minus f of a. So that's like your y2 minus y1. And then a plus h minus a, right? Take one move to simplify. So I want So I'll pause there while you're both talking. Are we okay? So let's look back on our overarching goal. I want to find the slope of the curve not across 2 points, but at 1 point only. So in that case, what do I want h to be equal to? As close to 0 as possible, right? Because I want those 2 points to not have, I don't want them to be separated. I want them to be same place. So instead of looking at this relationship here, I want to look at what happens as it approaches 0. I want to make that distance of separation as small as I can, getting arbitrarily close to 0 as I want. So pretty clearly, it's not continuous at where when h is equal to 0, because the function is not even defined there. But hopefully the limit exists, and if the limit exists, that is what's called a derivative. So this right here is, and I'll give you this in more detail in the next slide. This is the derivative of f at x equals a. And a piece of notation that maybe you've already seen, we're gonna use a lot here is this f prime of a. What that f prime says is, what is the value of the function? What is the derivative? What is the slope? Before we get into all those different ways we can use this thing, it's important to know where it comes from. And really, it all comes down to this motivation of, I want to find the slope of a thing that is not a straight line. Now we have the ability to do that. Any questions about this before we dive into it in more detail? And please, please, please ask me questions like this. I mean, we're going to be using this really for the rest of the semester, and for a lot of you, for a couple semesters. Go ahead. Yeah, so the derivative is, this, and you might see this called the difference quotient. And actually, I should be clear about something. The difference quotient refers to this part of it. Basically, I am taking the difference of two distances vertically. That's what the numerator is. Taking the difference of two distances horizontally. That's the denominator. And I'm dividing them. It's a quotient of differences. What the derivative is the limit. When I make that horizontal distance, that x distance, very, very small. Any other questions about this thing? All right. So I just gave you this bottom flavor here. Actually, I think in that with the example of f of x equals x squared, we looked at the top one too. But these are both pretty widely seen ways you'll see the derivative. Either I have some point A that I'm trying to make really, really point to some close to some point X, or I have two X values, A and A plus H, and I'm trying to make them arbitrarily close to each other. So this derivative f prime of A gives the slope of the curve at the point A, f of A. And here's another word you'll see a lot if you haven't already been seeing it. It also gives the instantaneous rate of change of f at x equals a. And while you're writing and kind of taking this in, I'll explain why the word instantaneous is important. So think about what we just did with secant lines in the last couple of examples. Those secant lines don't give you an instant rate of change or an instantaneous rate of change. They give you an average rate of change because I am by definition looking at an x interval that has non-zero length. I'm taking a value here, I'm taking a value here, and I'm averaging out, kind of like what we did with the rock. I'm averaging out values to find its speed. But if I use a derivative, I'm not taking an average. I'm getting the speed, or I'm getting the rate of change at this point in time, or this instant, whatever I'm looking at. I actually have a way to find the slope of the curve without looking at two places. And we're going to talk about this in with any pair of related quantities. So the one that I kind of gave you on my very first slide of the semester was one about speed. So speed and acceleration are some common ways to use derivatives. You'll use these with forces. Those you're going on to like mechanical engineering and physics, things like that. In an electrical context, you'll see this with voltage and current. You'll need to use their derivatives for certain things, but these show up a lot. So now I want to find the equation of the tangent line to this point, to this function at this point. So I could try the method I did with that first example where I got kind of lucky. Really, I cooked up that example so it would work. So where I was able to get that derivative. But now that you have the derivative, and I'll just remind you of it here, f prime of a is equal to the limit as, and let's try the h flavor here. The limit as h approaches 0 of f of a plus h minus f of a over h. Now, instead of relying on getting lucky with algebra, let's try to use this this difference quotient directly. So in this case, this whole thing I just wrote is general. What's the a that I care about here? Great. So yeah, what's my, this is my x value of interest. What other symbols am I gonna have to unpack? What's f of x? 3 over x. So I think based on those two things, I can start working towards finding this derivative. So not f prime of a, I want f prime of 3. That's going to be equal to the limit as h approaches 0 of, for now I'll just do this, f of 3 plus h minus f of 3 over h. What is f of 3 plus h? So 3 over 3 plus h minus f of 3, which is 1 all over h. So drilling down from general to specific. Hoping this limit exists. What can I do to keep trying to find this limit? Go ahead, Sebastian. How did we get 3 over 3 plus h? Right. Yep. So yeah, f of x in general is this function. So this is the function we're trying to take a derivative of. This f of x equals 3 over h, or f of x equals 3 over x. So what is f of 5? 3 over 5. What is f of 10? 3 over 10. What is f of a plus h, or 3 plus h? It's 3 over 3 plus h. Basically, we're just evaluating this function at my two values, a plus h and a. And in this case, my specific a value is 3. All right, so I got this weird expression here. I clearly cannot just plug in h or 0 for h because that won't yield me anything, but is there anything algebraically I can do from here? How do you guys feel about compound fractions like that? We hate them, right? How can I clear them? How can I get rid of them? I cannot cancel out those 3's. I can get them in the same denominator. Sebastian, do you have something? Multiply where by 3 plus h? So multiply this by 3 plus h. Is that okay? Yeah, I'm going to have to maintain balance here. But yeah, I think this is a good course of action here. So if I multiply the denominator or numerator through, I'm going to get 3 minus 3 plus h over h times 3 plus h. Did that do anything for me? So numerator, yep, that simplifies down to negative h over h times 3 plus h. And hopefully some of you are seeing that that was a big step in the right direction. Because this happens and I get this limit of negative 1 over 3 plus h. So my last two steps there? Oh, sure. So all I did was simplify the numerator. Can I evaluate this limit now? And I'm going to abbreviate this to, I believe strongly that you all, because you're here, can find the equation of straight lines if you have enough data. So the derivative's the new thing. Let's just concentrate on that. So the slope of this curve at that point is negative 1/3. And if I have enough room left, actually, hopefully I can make some room here. I'll remind you kind of what this curve looks like. If you think about what tangent lines are going to look like as x goes to the right, are those slopes, are those tangent lines going to have slopes that are positive or negative on the right-hand side of the y-axis? Maybe that question's a little too, maybe I need to wait on questions like that. Yeah, I'm going to hold that question for later. Any questions about how we got negative 1/3 algebraically here? Okay. So back to this thing. I'm telling you that the distance a rock falls is given by this thing. Now we have the tools to find its speed after 5 seconds. So we should talk about this. You know, we've been kind of, actually, I'll still getting into this. Let's write down the derivative again. F prime of A is equal to the limit as h approaches 0. And I said, like, I gave you two different looks of what the derivative looks like. I believe this one's more commonly used. It is no more valid than the other one. So start getting used to this difference quotient. Very important thing we'll use a lot, especially in the short term here. I'm going to re-express this as S prime because that's really what we care about. Actually, while I'm doing that, why don't I stop calling it A? What is the value of A that I really care about for what I've asked here? 5. So I care about what happens. I care about what that rate of change is at 5 seconds when t is equal to 5. S of 5 plus h minus S of 5 all over h. What is S of 5 plus h? Yep. And I'm very glad I did this at the start of class. Memory serves, that's 122.5. Okay. All over h. So I would love for this limit to exist so I can figure out what that speed is. How can I keep going to find this limit? Yep, I think that's a good idea. And then I'll kind of, actually, I'm going to save that. I'll ask you what you notice in a bit. But if I expand this, I get 25 plus 10h plus h squared minus 122.5 all over h. I know that 4.9 times 25 is 122.5 plus 49h plus 4.9h squared minus 122.5 all over h. So that does me some favors. And some of you see that I'm pretty close to being able to evaluate this limit now. I'm going to factor out an h from the numerator. I get 49 plus 4.9h all over h. Can I evaluate this limit now? What is it? 49. And I'll put one more step in here just to make it really clear. The limit is h approaches 0 of 49 plus 4.9h. Second term vanishes and I get 49 meters per second. And if memory serves, the very first time we did this, we took that average speed over that big interval of the first 5 seconds. I think it was about half that. I think it was like 24 meters per second. So clearly this is a lot greater, a lot higher speed. Any questions about how we got this thing? Go ahead. Oh, that's not an exponent. Oh, sorry. Thank you. That is an exponent. That should be squared. H squared. Is that what you're asking about? Yeah. Okay, good. Mm-hmm. We're definitely getting to that. But really, you know, by the end of the semester, we're gonna have so many differentiation rules, and they really all boil down. They all come back to this. They all come from this this relationship. Yeah, those of you who have seen the power rule, you can definitely verify that you'll get the same result there. Any other questions? Go ahead. Mm-hmm. Yeah, so let me kind of sketch this parabola again. You know, all parabolas sort of look like this, but let's say this right here. This point is, so this point will have the location 5, 122.5. But if I were to draw a tangent line here, bad, this slope, I am. Yeah, so graphically speaking, if I were to graph,
for the limit of that page, what is the 4.9?
yeah, why did that vanish? I'm sorry? Correct. So, and that's all. So here goes to 0. Yeah, if you look at this graph here, that value of 49, that's not a location that has any meaning to that graph. Like 49 is not the coordinate to some point on here necessarily. Is that what you meant?
No, it's the slope of the tangent line. But when we're looking at limit, 49 meters per second is the limit of the not the actual.
Yeah, it's the limit of this difference quotient. So yeah, it's and the difference quotient is the derivative. The derivative of this function. The derivative of this function is 49 meters per second, but only at that point. If I wanted the speed at t equals 3 seconds, we're going to do this. Go ahead.
This is at this point in time, you want us to use this our process instead of the individual.
Yeah, so I'll take that. Yeah, don't bring in color. Anything else? All right. Let's do part of this and I'll leave the other part for you. So same function for the distance here. I want to find the speed after it has fallen 450 meters. So any idea how we would do that? Start the same way as last time. So because it's brand new to us, let's do this. Awesome. I think I know what my f of t is. 4.92 squared. What else? Is a 450. F of a is 450. Okay. But there's something else we need, right? Yeah, that we do need a. So we'll do that. 4.92 squared. equals 450. And I'm going to rely on somebody in here to give me that value of time. 9.583 seconds. Do you have a question?
No, I was-
You were going to give me that? Okay. So, if I don't specify, I mean, three's fine. So I'm going to stop there. So we got the time. Actually, I have to say, so that's equal to A. And I'm going to leave this as an exercise for you. I'm not going to do it in here, but I definitely encourage you to do it on your own. Show that f prime of A is approximately equal to 93.91%. Hopefully the fact that I did that in 2 seconds on an iPhone calculator will let you know that something a little more efficient is coming your way soon. So I'll leave that part for you to practice. I think it's getting comfortable with this difference quotient thing is really, really important. So I definitely recommend you going through that one. Any more questions about this? All right. So let's close with this. I want to prove this function equal to A. So everything else we've done to this point, I care about a certain fixed value of X, right? But now I want to do something general. I want to find the derivative of this function when X is equal to something arbitrary, something variable. Really, it doesn't work any differently. So how should we get started? What is the derivative of a function? Slope? What's that? Perfect. How do I find that? Missing something small but very, very, very important. Yeah. Need that limit operator. So yeah, I mean, we're still going to use the same thing. In this case, what is f of A plus H? A plus H squared plus 3 times A plus H. Plus 5. And then f of A is just minus A squared plus 3A plus 5 all over H. All right, can I do anything with any of these terms? Yeah. So let's expand all the brackets first of all. And I'm guessing by now a lot of you are seeing, you know, kind of how these difference quotient manipulations go. So what, did that buy us anything? This goes away. I think I messed something up. Oh, I messed up something really huge. Oh no. Oh no, you guys. Now all the things that I crossed out are true. So I get the limit of 2 as h approaches 0 of 2ah plus h squared plus 3h all over h. Which comes out to the limit as h approaches 0 of this 2a plus h plus 3. So what's my final value for this derivative then? 2a plus 3. So like with everything else we did prior, you know, I just found the derivative at one place. Now, if I ask for what the slope is when x equals 1, could you tell me? Or x equals 10 or anything, right? So this is something you have. Now this is a lot more versatile. I can find a derivative at any point now. Is there any difference between the way we developed this and the way we would have developed it if it was like find f prime of 1? No, absolutely the same. Got some more symbols to keep track of, but really it does not work any different. Any questions here? And we got like 3 minutes left, so just to show why this is useful, I want to find the equation of the tangent line. Same function at that point there. So I have to go through all the difference quotient stuff to figure out what f prime of 2 is. Now, the whole point of, and I'll write this a little differently than we just did, but we have this now. This is something we know we can always use. And we'll talk about this in more detail on Friday, but f is a function, but f prime is also a function that's related to f in a very specific way. So I have this function f prime of x, and now I want to find this value, f prime of 2. What's f prime of 2 equal to? 7. It's equal to what happens when you evaluate the function at x equals 2. So I got this value. Now I want the equation of a tangent line. How do I find the rest of that equation of a tangent line? So y equals mx plus b. Because we're new to this, it really is worthwhile to make sure we know what all of these values are. This 7 here I just found, what does that represent if I'm trying to find the equation of a straight line? M, right? Because 7 is the slope. That's what the derivative gives you. It gives you the instantaneous rate of change or the slope of a curve. So m is equal to 7. How about x and y? 2 and y is 15. So that gives us that b equals 1. And my slope of a tangent line is y equal, or my tangent line has the equation 2x plus. And one thing I'll encourage you to do just to kind of convince yourself and see how all these things behave is graph line and f of x together. And assuming we did that all right, you should see a curve, you should see a parabola, and you should see a straight line that is tangent to it. Anything else? All right, if you turned in the hard copy of the quiz, stick around and I will get it back to you.